Yes. Hello all. Welcome to Know Mam. When today is a great day, we have very wonderful person, Mr. Blaine, with us. So, for the sake of audience who are not aware of Mr. Blaine, whenever like if somebody wanted to learn and do stuff with data science and anything related to machine learning, or if you are a student, if you are a professional, if you want to research and learn something really good about data science, machine learning and all, you might have come across with Mr. Blaine. So today we are introducing Mr. Blaine on our new Know Mam YouTube channel. He's a true tech leader with over 35 plus years of experience in the field of data science, machine learning, and understanding the technology inch by inch by researching, experimenting, and his valuable contributions, not only just experimenting or learning or sharing his knowledge, the his expertise helped many government projects, R&D projects, what not, like he is like true legend in this particular area. He have no cherished that tech in to the next level as a founder and chief data scientist at EAF, and wherever he got one position is a career timeline, he became the definition of that position. So that great man gave us a time slot to present his thoughts on outlier detection and one specific talk related to data science. We are truly honored today having you on with us, sir. So the stage is yours. Just share us a little knowledge, no piece from the version which you are consider having. So no, pour us little drops
Great.
from your version of knowledge.
Very good. Well, thank you for the kind introduction, probably too kind. Um, so I'm going to talk about outlier detection and show something kind of interesting using an embedding method called UMAP. Um, I wanted to start a bit because a lot of people, when they come into data science, they quickly learn about data cleaning. Uh, and when you think about cleaning, the idea of cleaning is to remove the bad, take away the dirt, the soil, unwanted. Um, and so people are taught about finding and removing outliers. The problem is it's a misconception. Um, in fact, in many cases, outliers are real. They're not bad. They're just in an unusual part of the distribution. So distribution might have a long tail. The ones out in the tail are still real data. So the question becomes, what's the right way to find outliers, and then what should we actually do with them? And so it's not so much cleaning as it is we're trying in data science or machine learning, we're trying to get the best model to solve a problem. And usually it's a business or a technical problem. So if you have outliers that are a small percentage, um, and your problem is to make good predictions as much time as possible. So these outliers that might be 0.1% or 1%, they can have a big impact on your model. And you want a model that does really well on the 99 or 99.9%. So if we remove the outliers and build a model without them, we can get a better model for the majority of our use case, our business problem. But it's not because they're bad or not real. It's that they have excessive impact on what we're doing, and we may not care about them very much compared to the other 99%. So I'm going to describe today a problem I worked on. Uh, and basically, the idea is you trade maybe not predicting the long tail of the distribution to do a better job in the bulk of it. But for the business case, that's good. So I'll give a quick introduction. This picture is the exhaust system of a diesel over-the-road truck. And whether you know or not, these exhaust systems are very complex because diesel engines create a lot of pollution called NOx, nitrogen oxides. And inside there is a, uh, a catalyst. There's multiple catalysts. And there's one here called the SCR. And the SCR works, it's a metal-based ceramic catalyst. And what they do is you put in ammonia, and you do that by injecting a urea dissolved in water, and it vaporizes and creates ammonia. The ammonia bonds to the catalyst. And when the ammonia is on the catalyst, it is able to reduce NOx to nitrogen. So to control the exhaust system properly, you need to know how much ammonia is in the catalyst. Uh, and there's different schemes to monitor this, but if you put in too much ammonia, you get ammonia coming out the exhaust, and you might have even smelled that at some point. If you put in too little ammonia, you get NOx coming out. So it's a balance, and so you need to control it. So you need a way to know, where am I? So this problem I worked on was monitoring this catalyst, and it's complicated chemistry, but it all boils down to how much ammonia is in the catalyst. So uh, very quickly, there's a very interesting technology. These pictures on the right are a cylinder. This is a radio frequency simulation, and the cylinder is the catalyst. So that's the tube in the exhaust. And these are those pretty colors are slices showing the radio frequency energy. And it turns out this catalyst it's a dielectric material. It's a ceramic. And we can insert probes or antennas, if you will, and we can excite it, and we can measure how much of the radio frequency energy is lost by the dielectric material. And we can do that at a whole range of frequencies. So the picture on the left shows it's a return loss chart, like on a network analyzer. We're measuring how much RF energy gets through the catalyst at different frequencies. And it turns out, if we look in detail, so there's 2 points down below, F1, F2, at those two frequencies, there's very different energy in the catalyst. And the shift, the blue is with ammonia, and the orange is before the ammonia went in. So we can monitor all these different frequencies and uh, try and determine from that how much ammonia, because the more ammonia we put in, the more the pattern changes. So my project was to use machine learning to take data from a dynamometer test setup that had laboratory instruments to measure all the ammonia, all the other gases, uh, temperatures, pressures, what was going on in the engine. We had all these data, and we had the radio frequency measurements from our sensor. And we were trying to build a machine learning model to interpret the data. And here we ended up with about 100 features, which are the different measurements of the frequency and the amplitude. So on the previous chart, where is each peak and how big is it? And sometimes how wide is it? Because that measures the energy loss, how sharp the peaks are. So we can measure a lot of frequencies, and this is in the gigahertz range. So there's we can measure down to kilohertz resolution, so we get lots of data points. So we break that up into about 100 features, and then we measure at different conditions, different temperatures, different engine loads, different ammonia injection rates, et cetera. And we get data to say, at all these different conditions, here's the ammonia that was in the catalyst, and here's the radio frequency spectrum. Can we build a model that, from all these features, predicts the ammonia? This chart, by the way, is what's called a parallel coordinates chart, and it's basically each these V's up here are the variable. That's each feature, And the range of these features is over the entire data set. And you can see there's patterns, when some features are high, other features are low, but it's very, very complicated. Um, this is an interesting way when you have a large data set with many features. If it's a tabular data set, you can put it into this parallel coordinates plot and get an idea of what you're looking at. This, by the way, I used this thing called HighPlot, which was open source by Facebook. I'll come back to this later. Just what is it? It's a way of looking at every bit of data we have in the model that now we're trying to interpret with a machine learning model. Uh, so in working on this problem, it became obvious that we had outliers. It's a very complex problem, physics and chemistry, variations in temperature, gas concentration. So I started looking into outlier methods. And one way you can determine outliers is you can use a clustering algorithm and then try and find outliers that are unusual compared to the clusters. UMAP is a dimensional reduction algorithm that uses a manifold approximation. And you can take a large dimensional data set and reduce it to any number of dimensions you like. Um, and then you can work on the lower dimensional data. Um, so uh, the clustering algorithm itself doesn't give you outliers. It gives you a lower dimensional space that you're hoping makes it easier to find the outliers. Because if I just go back for one moment, it's very hard to tell in this plot what's outlier and what's normal because everything is varying quite a bit. So, a very common method is called local outlier factor, which is possibly very useful when you have cluster data to find things that are unusual compared to each cluster, meaning the clusters are local, what's an outlier? So if we take the sort of a standard UMAP, we use the default parameters, we apply it to this data, out of a few tens of thousands of instances, we got about 1,962 that it said were outliers. Uh, so that's an interesting result. Uh, and we tested that by removing them, and the results were not completely satisfactory. So if we look at UMAP, though, there's something interesting in UMAP, and I just give the references here. And Cody, it's perfectly fine to share the PDF if you choose to. Um, but
Yes, sir,
you can
definitely.
read you can read the UMAP documentation. You can read the paper. Um, there is a hyperparameter in UMAP. Uh, Most people think of clustering as unsupervised, but it turns out there's almost always something you have to choose, like the number of clusters or something. In UMAP, one of the features is called the op mix ratio parameter, uh, and it is basically controlling sort of how tightly it tries to group the data. Uh, and if we use the defaults of UMAP on MNIST, and almost everybody's familiar with MNIST, it's the handwritten digit data set, we get this result. It's quite satisfying. We can see in each colored region there's some points of the other colors, which means there's some mistakes being made. Um, and that's curious. It makes you wonder about, are those bad data or what's going on? Um, but it turns out if we adjust this parameter, this op mix ratio, if we put it to a low value, we can still see the bulk of the digits in the different colors. But now we see these unusual points are almost all outside. So now we find outliers in UMAP, and there are in fact outliers. In fact, there's probably errors in UMAP, or not UMAP, I mean MNIST, excuse me, in MNIST. But there are also unusual cases where somebody wrote a 5 and the top of the 5 was disconnected. Somebody wrote a 1, it was very tilted. Somebody wrote a 0, they didn't close it. So there are outliers, and it can make it challenging to perfectly detect the digits in MNIST. The reason I show you this, though, is this op mix ratio. If we put it to a low value, we can change UMAP from a good clustering algorithm into a pretty nice outlier detector. And that's what I did. So uh, these are the data I showed you earlier. Uh, I embedded them in UMAP, and I played with the op mix ratio, and I put it in 3 dimensions. This is a 2-dimensional view of a 3-dimensional cloud. The colors here are the different temperatures that we did the tests at, and temperature makes a big difference to this catalyst. You can see they tend to group, but it's kind of noisy. Uh, and in the spirit of the MNIST example, so if I go back for a second, if we said this is a cluster, if I could draw a boundary around this cluster and around the other ones, and then look in the outside the boundaries, I'd have a good chance of finding these outliers. So in that spirit, uh, uh, what was done is, I'll skip that for a second. um, I applied basically outlier detection to this 3-dimensional data. And if I use local outlier factor, like I showed you before, it finds these points, but they all seem to be within the data set. And we already showed from before that using this result did not improve our model. So I decided to take um, a different look at this. And let me just go to the next one. Again, I'll give you the reference so you can look this up. But I said, this cloud, because the 3-dimensional cloud, it looks sort of like egg shape. So I said, look, I can fit an ellipsoid around this, and I can look at the radius and look at points that are outside. So that's how I'm going to find these outliers. I'm going to fit the data with a 3-dimensional shell and then set a threshold and look at what's outside the shell. And I think this one I can show you. So if we turn it, you see now these outliers that I'm finding are out on the edges. So they are true outliers for this point cloud. Uh, and when we use this result, and I'll just show you, if we go back one slide. This is the threshold of 0.5. This has to do with the radius. It's kind of arbitrary, but uh, it has to do with what radius we look at. And this is a different threshold. And so you see, we can threshold and see more or less outliers. So we have an adjustment we can tune. So what we did was we computed the outliers using this method, use UMAP with a low op mix ratio, fit a 3D shell and look for points outside the shell. And when we applied that, uh, this is kind of interesting. The bright pink here, those are the outliers. And in certain variables, you could say, oh, they're very high or very low. But in general, it's very difficult in this space to see that they are outliers. But outliers they are. And when we removed them, we got percentage point improvements in our prediction in the model, which was a very pleasing result. In data science, we can work for weeks to get half of 1%. So we got multiple percentage points improvements. But I wanted to show this to you. If you compare to the previous plot, these plots are quite interesting, but in these complicated high dimensional spaces, it's very hard to look at this representation or any sort of low dimensional representation and find outliers. This method that I've shown you is a way we can basically take an embedding algorithm like UMAP and adjust it to turn it into a good outlier detector. But we have to be crafty about it. If we just use normal outlier detection like local outlier factor, we still don't get very good results. Um, I wanted to give you a little bit of insight. Um, if we look at the entropy in the data, uh, and entropy, if you've ever looked into what entropy means in the data sense, it's related to the information content. This comes from information theory, from Shannon's work on information theory and how entropy is related to the amount of information we can transmit. Very interesting result when we use UMAP in this way. The entropy of the embedded space, the blue, it's actually higher than the entropy in the original data. And I discussed this with Mr. McInnes, who's one of the authors of the original UMAP, and he said, actually, that makes sense because uh, in the topological sense, when we set op mix ratio low, we have a more disconnected space, and that means the entropy is actually high. And what I've just shown you is we've extracted the information about where are the outliers. Whereas when we set the op mix ratio low, we get very nice clusters, but the entropy is actually lower. So this shows that finding these outliers is actually related to the entropy of the data, which is related to the information content. I thought that was a very, very interesting and elegant result. Um, and that's the gist of my talk. So that was very quick. I introduced a lot of concepts. I talked about some physics and chemistry and a catalyst. I talked about radio frequency measurements. I talked about high dimensional spaces and using dimensional reduction. I showed some limits on standard outlier detection, and I showed how we can basically use UMAP in an intelligent way to find outliers and make an improvement in a very complicated machine learning model. So thank you
That is
for
very great.
the
That's
chance to
very
present that.
thank you so much. Pleasure is ours always. Like that is very great, short and great. So we have one question from the audience, Glenn.
Sure.
So can you give us some suggestion? Can you give us some
Would you,
suggestions or points that we have to focus on a beginner? Like if a beginner wanted to, start their career in terms of data science or machine learning, what are the things they wanted to they need to focus, and how can they get started with, is one question came up.
yeah, it's a good question. So uh, I'll answer it in kind of a strange way. Uh, Cody, why don't I stop sharing for now, and if we get a question about a slide, I'll come back to it.
Okay.
Yeah, a little better for your viewers maybe. So how to get started in data science. So um, the things I showed today, it's a good example of we have lots of tools, and people get concerned, which tool should I learn first? Um, and they get really focused on tools and using tools. They get excited. They find a new tool, some new algorithm. They want to use it. Um, my view is a little bit different. Data science is just another toolbox that you can draw from to solve problems. So the real starting point is problem solving, and the starting point of problem solving is asking a lot of questions. So if we look at this case, if you just gave me these data as a tabular data set, and I didn't know anything about that we're looking at frequencies that we're trying to predict a concentration on a catalyst, that temperature might matter. It would be I could apply all kinds of different models and get different results, but I would have no idea what was happening, where the insight was coming from. So in this case, I spent a lot of time discussing the problem with the customer to understand it a bit. Oh, it's on a diesel truck. It's controlling emissions. It's a catalyst. Here's the variables we use to understand what should be in the model and why it might actually even work. So the first point is to practice engaging with stakeholders and asking questions until you think you understand the problem. You don't have to be a subject matter expert, uh, but it's very important that you be able to find the subject matter experts. So from that, the nuts and bolts are that uh, in machine learning, people they quickly get sort of consumed with, do I need to know a lot of math? And uh, to be honest with you, it's helpful to know to have at least some concepts of linear algebra. So when somebody shows you a matrix notation, uh, for solving a like a linear regression problem in matrix notation, it's a very simple equation. Uh, you have some intuition Not that you could write it out yourself and do it immediately, but you can understand what you're looking at. So a little bit of linear algebra up to the point where you understand like matrix multiplication, matrix inverses, transpose. So these are things that show up in machine learning. Then the other thing that basically you need is to understand calculus, and the level you need to get to is to understand what is a partial derivative. Um, so that's like second year calculus. And again, not that you could take a given problem and start writing out all the equations in calculus, but that when you're looking at them, we talk about gradients, we talk about slopes, uh, and we talk about minimizing things. You have an intuition in calculus. Uh, uh, After that, so those are the two things. I mean, there's lots of math involved, but those are the two things that will help you with your intuition when you're actually understanding methods. Uh, so, and a little bit of the jargon, what is a gradient? Sometimes, like even in a gradient boosting algorithm, which everybody uses, uh, gradient boosting algorithm uses the second derivative, which is called the Hessian in calculus. So it's helpful if you see this term Hessian, you know what it is. So, but you don't have to be able to calculate yourself. So up to that level. So, it's like, uh, a freshman level linear algebra course and a couple second year calculus, you'll be fine. And again, not expert, just to understand, have the intuition. Uh, then the biggest thing not to do, so this is, and then I'll let you ask another question. Um, the thing you don't want to do is don't start right away with the most complicated thing. So don't jump into deep learning. Uh, don't even jump into something like even gradient boosting, or maybe don't even touch random forest. Start with the simplest thing that could solve the problem. So if you're working on a regression problem, use linear regression. If you're working on a classification problem, use logistic regression, or maybe a classification tree. Um, and from there, what you'll see is maybe it doesn't work well. Work on a problem and start to understand, well, why doesn't it work well? If linear regression can't solve it, why not? And that'll make you think about what's actually happening. And if you can get comfortable with these basic methods and how to make them better by maybe working on some feature engineering. And by the way, feature engineering is tied completely back to this first thing about understanding the problem. You can't really engineer features if you don't know where the data even come from. It's silly. I don't like these approaches where people use automatic feature generation. They get all this gobbledygook. I don't believe in that. Um, so if you work with simple methods like linear regression, logistic regression, and use logistic regression as a classifier, or use a decision tree as a classifier, and use linear regression as a regression model, and then figure out why they don't work on your problem, and then um, get a deeper understanding. Okay, what are the data and what might be happening that's preventing these models from working as well. Once you have that comfort, then you can move on and tackle almost anything. So long
Yeah,
answer,
that's
but it's
exactly yes. Yeah, like you rightly mentioned, no, like so I spoke with lot of college grads, couple of my seniors, there are a lot of people who had invested like 2 to 3 years of valuable time understanding these algorithms and like how it is working. What exactly the linear regression, logistic regression, k-means clustering. So what is svm, what are the things like we need to go through. They were trying to understand, and like they are spending lots and lots of time. So that is the one way I saw. So I some things I saw in some recent college grads, like they were not aware like what exactly what simple linear regression is. So all they need to do is like in GitHub there are some repos. So they have a proper model, or some say some Jupyter notebook which is built with all the detailed steps. They're just trying to execute step, executing the things, and they're generating something.
Right.
So, like you rightly mentioned, right? So, what might be the approach? Like, is there any really need to spend like 2 to 3 years of time, or a college grad? Like, what exactly he need to change his perspective to get into data science? Like, what kind of efforts he need to put? It just what matters. Like, you are a veteran in this industry. So if a fresher coming to you, and if you are, for example, say in a scenario like you are entering a candidate, what you'll see in that candidate, like at the beginning, and
Yeah. Well, that's yeah. It's a great
yeah.
question because you know a common question might be, okay, here's a problem. What algorithm would you try first? And let's say it's a time series problem, and somebody says, "Oh, I'd use a neural network with a LSTM, and or maybe even a 1D convolution," and that would be the worst possible answer, right? Because um, I'd say no, that shouldn't be what you try first. Um, Even it's a time series problem, you can convert that to a linear regression problem quite simply, and then make an initial look at it, and that'll give you a lot of insight into the data. Um, and uh, uh, and another answer, they might say, "Oh, well, I would just throw auto arena at it and see what it looks like." That would also be a bad answer because I see a lot of people, they're trained, "Oh, use ARIMA, it's great, it works for everything." So now we have auto ARIMA, so it automatically finds the parameters for ARIMA, or it supposedly does. So they take a time series problem, they have no idea what it's about, and they put it in ARIMA, and they seem to get good numbers. And they say, "Yep, that's good." And it's like you have no idea what that model might do in the future. So again, what I want to hear from people is, well, I always make a baseline, and my baseline is a simple model. Here's what I'd use for regression. Here's what I use for classification. Then I analyze, the problems. I think about feature engineering, and then I consider what models might be more robust. But I always have my baseline. Uh, and so, people, I think, maybe want to impress somebody in an interview with all these algorithms they know. But that's not a good problem solving method. So, I would actually look for the opposite. And you mentioned, this is a point I can't resist. You mentioned they learn all these algorithms. And one of the things that I'm so surprised by is there's still so much discussion of support vector machines, SVM. And
Yeah.
I'll be honest with you, early on in my work, I thought I liked SVMs because the idea is so elegant. It's a beautiful concept. Uh, and unfortunately, I've not found a single problem where SVM ever works. Um, so if there's one thing you could ignore and don't learn that support vector machines. It's a waste of time. Plus, it's very computationally intensive, so it just takes up a lot of your time. But I'm still surprised. They put this in the curriculum at school. It's like learn support vector machines. Uh, I've seen no practical problem ever solved by a support vector machine. So, if you want to work in the real world, don't worry about it. You can do more with linear regression than you can with SVM. Uh,
Okay. Yeah. One more question. Like, as you rightly started in your presentation, right? You quoted like there is no waste data. Like when we are cleaning the data or something, so there are no waste parameters or useless parameters. Like at that point time, in a comparison with the other parameters, those are not required. Like, what are the precautions or the first steps when you're dealing with the data cleaning, whether it regarding
ah,
pandas or something. So,
right.
what might be the ideal approach to start with any sort of data?
Well, in machine learning, we're living in a sort of a statistical universe. We're building statistical models. And so one kind of core concept. It's sort of a math concept, but you don't really need math, but it's kind of an ideological concept. Is that everything is a distribution. So every variable um, has a distribution. Now, some things are quote categorical, so they only have specific values. That's fine. But the majority of real data are continuous and they have a distribution. Uh, and I'm constantly surprised when I see people do a data analysis and they don't look at the distribution of all the variables. Um, so, the first thing to do is develop your own way, whatever you're comfortable with, to visualize the distributions of all of your features. Because each feature may have its own shape and its own possibility of outliers. Um, but it just gives you intuition about what's in these data. Because if you think about all the features in a model, you're combining them in some sort of mathematical combination. So these distributions are being mixed together to form a distribution of the dependent variable. So if you're trying really hard to get a good fit of the dependent variable, wouldn't it be a good idea to look at the distributions of every input first? Um, it's also a great way to discover if there are problems. Um, so, I would always do these basic visualizations uh, of the distributions first before I worry about missing data or anything else. Um, and then it might spark some thoughts or find something strange. Maybe there's a couple of features that are very unusual. Uh, then, there's a couple of other problems that come up really quickly. And one is what to do with missing values. Um, and missing values are real. They come in everything. Even from a laboratory experiment, there ends up maybe being missing values. The sensor had a glitch, so for a few moments you miss some data. Um, so back to my first point, throwing away data should be your last resort. So removing anything, you should wait as long as possible. That should be the last thing you do. So if you're not going to throw away the instances with missing data, what shall we do with them? And I think it's very much a disservice that people are taught use mean or median imputation, and boom, off you go. Uh, there are many more sophisticated imputation techniques that can do a better job. One that I find very useful, but it's challenging to apply. It's called MICE, multiple imputation with chained equations. Um, and uh, applying mice, there's packages in Python, packages in R. It can be a little challenging to understand what's going on. However, using mice on your data set and figuring out why it doesn't work or how to get it to work actually forces you to look very closely at what's going on in your data. So it's actually a good investigation tool. But there are other ways. There are many other ways to do it. Uh, you can literally run regression models on each feature and fit it to everything else to impute. And that can often be a lot better than mean or median. Um, and if you think about it in the distribution sense, and this is another thing that's frustrating to me. So people take a data set and they have some variable with a bunch of missing values, or maybe two or three, and they use impute the median. Okay. If you look at the distribution of your features after you do that, there's a spike because the median, all those points go to the median. So you have a distribution that's no longer smooth. It goes like this, and then up, there's a spike, and then it comes back down. Statistically, that's terrible. You're creating a really abnormal distribution that you're putting into a model. So if you think about it from a distribution sense, using mean or median is often not very good. So step one is look at your data. Step two, think about how to get the missing values, but don't use the easiest way. Really think about what you're doing. And then step three is as soon as you can get the data into a semi-clean format, make a baseline, linear regression, logistic regression. Then start the rest of the work, feature engineering, removing outliers only after you have a data set and have a baseline. Uh, so there's a lot of other things you can do in investigation. People love to do the Seaborn pair plot. the,
Yes.
uh, the problem is in real problems, most two variable relationships don't have that much meaning. The toy problems we get like the cars data set. Oh, you get all these nice correlations that go this way or this way. That's great. If everything was correlated to in a 2 by 2 space, you could write down the solution in a notebook page. You wouldn't need a machine learning model. In most real data sets, the relationships are complicated. So pair plots, they're interesting, but rarely are they that useful. Um, the other thing that people do a lot, and I sort of suggest them, oh, okay, it's fine to do it, but ask yourself why, is everybody does the correlation analysis because they're taught this, right? They make a heat map, the correlation chart, and they go, oh, this is highly correlated. And I get this question a lot. Somebody says, oh, I'm working on a problem and I have a 35 features and two of them are correlated at 0.8. Should I remove one? I go, you're crazy. First of all, nowadays, um, hundreds or even thousands of features are no problem. So dimensionality reduction shouldn't be just for the sake of dimensionality reduction. If you don't need to do it, don't do it because you will lose information. So if you're doing a correlation plot with the idea, I want to reduce my dimensions, why? If you only had 35 features or even 100 features, you could just build a model. So why, before you even build a model, are you trying to reduce the dimensions? Why? Because they're taught. They say, oh, you should look at dimensionality reduction. They do PCA or they do something else, or they do a correlation plot. Second thing is people get so worried about multicollinearity. They say, oh, these are correlated at 0.8. I should take it out. That is not multicollinearity. Multicollinearity is near perfect correlation. So unless you see, correlation of 0.99, it's not really a problem for most models. So you really have to ask yourself, what are you doing with this correlation analysis? People waste a lot of time on it. So I see them, everybody does the same thing. They make a pair plot, they make a correlation heat map, they say these are highly correlated, maybe they throw some out, and then they build a model. It's totally, I would never do it that way. So if you're not going to use the results of the correlation analysis, and 99.99% of the case studies I have seen students do, they don't use it, they just present it, then why do it? So
Okay.
that's my that's my quick summary of what to do and not to do in this first phase. I mean, it's really pretty simple. Look at your data and think really hard about what to do with missing values, but then get a baseline before you throw anything out or you reduce dimensions or any of that other nonsense. Get a baseline.
Okay. With that, I have one last question for today, Blaine. Sorry if I'm taking too much of your time.
No,
So
no,
this
my time is yours.
thank you so much. That is very kind. So, like, whenever, I'm again, I'm iterating this. I used to speak with a lot of people, whenever I get them in workshops or meetups. So, I used to, listen. People, one person is telling, like, I completed data science course in 1 month and I got a job as a data scientist. I have I have heard people saying, like, I'm spending more than 3 years still I'm learning few things and I'm not landed in any job. So as a beginner or a person with no knowledge on this data science domain or not. So what will be the ideal time we need to spend as a like in a very generic way. So to understand like whatever the topics and math you have mentioned and one programming language, ideally Python or R or whatever, so, what will be the ideal approach and ideal time to have a proper, sustainable career? It's not like, I don't know. It's common with everyone. If every a lot of institutes and training institutes also doing the same stuff. Like you come with join others, like 1 month will teach everything and will land you in one job, and tomorrow it's a question of survival, right? So I just wanted to understand like the ideal scenarios in terms of learning, in terms of time period, in terms of efforts what they want to put, to just started with, and moving from 0 to 1. It's not like
Yeah,
expert like you. We only get a chance to meet experts like you in once in a lifetime, because it's not a a simple thing. But moving a step 0 to 1, what efforts it needs.
yeah. So uh, it's a good question. It comes up a lot. Um, in terms of the time frame, uh, first of all, anything really short, like a month or 6 weeks, that's not really realistic. Um, and so, just beware of anyone that sort of makes that promise. Um, to be honest with you, even like a PhD in physics couldn't become a data science in 1 month. That's just not feasible. Um, so you have to give yourself the time to learn. Um, what's the optimum time? I've been involved in helping a few programs and 6 or 8 months of work. Um, and but what I see is it depends a lot on the starting point. Um, if someone comes in from technical background, 6 or 8 months may be okay. But we have a lot of people, they have maybe business background, a business degree, or some other, non-technical space, and or maybe they have some finance background, but they don't have a deep technical background. And you know, in those cases, it's highly individual. Some people have pick things up quicker. So uh, it, but I think it takes a bit longer, and people tend to they kind of go too fast. So this is where you know thinking about what should I do to get a foundation and then start learning advanced topics versus a set path where you quickly start doing things. You're learning statistics, you're learning model building, you're learning this. It can be overwhelming. Second thing is, uh, you know, if you're in college, that's great because you have lots of interaction. So if you start learning machine learning, even if you're not in a machine learning program, maybe you're in physics or chemistry or something, you have a chance to maybe take a few extra courses and you have a chance to work with people. That interaction is extremely important. So if you're going to take a boot camp program, uh, look for something where there's people you can interact with, that it's not just online. All you do is fill in the blanks and say, check, I finished that course. Because what happens is you won't really learn. You'll absorb a little bit. So you need that. You need to work with people somewhere if you're going to become a data scientist. So now, why did I say that? Remember what I said? I started with, it's really about problem solving. Problem solving is about asking questions. Okay. If you're just looking at your computer screen, are you asking those questions of a stakeholder? No, you have no interaction. So look for something where you have people to interact with. You can bounce ideas off, brainstorm, ask questions. Um, the but I think the most important thing. So if someone comes to me and they want to work, um, the the first thing I'm going to look for, first of all, I'm going to look at your LinkedIn. I'm going to look at your GitHub. It's another thing I'm shocked. People say they want to become a data scientist. They're trying to find a job. They don't have a legitimate GitHub. That's crazy. Okay, build up your GitHub. That should be your showcase. Okay, and your LinkedIn should be complete. It's unprofessional if it isn't. So it should be complete. It shouldn't be strange. It shouldn't have gaps. It should explain what you've done. Uh, but the single biggest thing after those sort of entry level, givens is projects. You need to show me you've done projects. And these projects need to be not a toy problem. I want to see original projects because I'm a big believer in project-based learning. So whatever tool sets you use, you pick Python, you learn pandas, you learn sklearn, maybe you learn Keras for deep learning. Show me how you were able to use these things and complete a project, including the business analysis and next steps, uh, pros and cons of your approach. Uh, don't just show me a report where you did an EDA and built a model. That's not a project. That's a task. So do some independent projects, complete from end to end. Find the data, analyze the data, understand where the data come from, define the problem. What is the problem you're going to solve? And then build up a methodology and then show you do it. Um, show that you can have some structure, show that you can ask questions, show that you can actually communicate results. It's another big problem. People learn all this technology, they have no skills to communicate. In the real world, we need to communicate results. We have to write reports. We have to send memos. We have to make papers. So complete projects. Um, so to me, looking at your project portfolio is more important than how you got there. If I believe you can do independent work in data science, then the rest is details. But if you show no evidence you've ever done anything outside of a class exercise, then it doesn't really matter how you got there. You're probably not ready.
Yes, absolutely. Yes. Yes. So that's all the questions I have for now, Blaine. I have
Great.
to tell you, like, I can't, thank enough for you for your valuable time. For sure, it deliver an informative and engaging talk. By answering our questions and presenting, and more than any of thing, giving us your valuable time and taking us into the world of data analytics with your enriching experience and all, like, this is very very great. With this, like, I wanted to extend this for further, like, not at this time, but for sure I'll reach out to you next time to present and teach us, some can it be pandas or any some basic ML model, through demo or workshop, for everyone. Today's like expert talk. So for everyone, if a college grader, fresher, who wanted to get started with or something, from beginner level to advanced level, expert data scientist. So everyone to understand, if somebody is already expert, then to refresh, their skills and all. I had to request for the demo or workshop kind
Sure.
of thing. So that I just wanted to tell you, and again I'm reiterating it multiple times, like, we are very very glad to host you on our Know Mam platform. So definitely, like, very great have you here, Blaine.
Well, thank you for having me, and I'd be happy to come back and do something hands-on. So we can discuss that offline and find a time and a topic. But as you know, I actually wrote the book, The Pandas Workshop. So I uh, I
Yes,
probably can
yes.
give some tips and insights into pandas. So maybe we'll talk about that.
Definitely, definitely. It would be a
Okay,
really
great,
great help. Thank you. Thank you so much for
excellent.
your time,
All right,
Naveen. Thank you,
thank you. All right,
audience. Yeah. Bye bye. We'll meet
all right.
again.
Bye, bye now.
Yes. Thank you.